Hello, everyone. My name is Fengbin. Currently, I'm working at Ant Group as a software engineer. I am a Ray developer contributing to GCS and placement group. At the same time, I'm also a user of Ray, based on Ray to realize the application of operational research system. Today, I will share with you a typical application of operational research based on Ray, online resource allocation. Before introducing the concept of online resource allocation, let's take a look at a business scenario. Recommending coupons to users is a typical scenario of a recommendation system. The problem to be solved is how to maximize the total sales volume of the platform when the stock of some coupons is limited. Let's take a look at this table. It shows the increase of user purchase rate bought by coupons. The order of users coming is user 1, user 3, user 4, user 2. When there are only 2 coupons in total, the traditional way to maximize the total sales volume is to elect coupons based on first come, first served. In this way, user 1 and user 2 get coupons, while user 3 and user 4 have no chance to get coupons. In the end, the increment of coupons platform sales is 0.3. Based on this table, the severe uplift is higher for user 3 and user 4, and a better way to allocate coupons will be to give them to user 3 and user 4, so that the overall revenue of the platform is maximized. Through this business scenario, let's take a look at the definition of online resource allocation. In the recommendation, search, marketing, and advertising systems, online decisions need to consider performance indicators such as click-through rate and conversion rate, as well as restrictions like capital cost and traffic. Online resource allocation is about maximizing the overall ROI under the concentrate of limited resource. Online resource allocation system is a trade-off between user personalization and group control. It needs to match the appropriate resource online for each incoming request while considering the limited resource available in order to maximize the revenue of the whole system. The system needs 2 capabilities. The first capability is to consider the user's performance and decide the resource allocation request quickly, which requires millisecond delay. The second capability is to maximize the overall ROI under the constraints of the limited resource. Combined with the case of coupons, let's take a look at the abstract model of online resource allocation. In an online resource allocation system, it is necessary to match the appropriate resource online for each incoming request, while considering the limited resource available in order to maximize the revenue of the whole system. In the coupon case, the subject of a request is the user, and the resource is the coupon. For each user I, the platform can estimate the revenue value CIG of G coupons and choose one of them to push to the user. When there are no resource constraints, every online decision is choose the one with the largest CIG. When there are resource constraints, such as each coupon G having an inventory limit, the optimal solution is no longer so easy to get. Suppose that there are K resource constraints, BK, in total, and each user I is given XIG copies of a coupon G, each of which will consume MIGK from the case resource constraint. Then the online resource allocation can be modeled as an LP problem to solve for the decision variable XIG, which maximizes the overall revenue under the global resource constraints. And the optimization objective is just like this. And the constraint condition is just like this. There are two difficulties in solving this LP problem. The first difficulty is large-scale problem solving for industry application scenarios, such as recommendations, search, advertising. The variable scale of the problem is often 100 million users multiplied by 10,000 candidate set, and the resource constraint scale can exceed 10,000. The second difficulty is that the future information is unpredictable and the global optimal solution can't be determined in advance. Next, we will introduce the overview solution. We provide a two-stage modeling scheme. In the first stage, the personalized requirements of users, such as click rate, rate of rate, conversion rate, are considered in the model training, and the model is used for online scoring. The second stage is to optimize the operation according to the scoring results of the first stage. Today, we will mainly introduce the second stage of work. The core of the second stage is operational research, which mainly includes three parts. The first is integer programming modeling. The second is online software. The third is online re-rank surface. This scheme has three advantages. The first advantage is that the regulation effect is guaranteed by theory. We have developed a set of efficient algorithms with theoretical guarantee. The second advantage is the adaptive control ability, which can adapt to the changes of the first stage model, flow, and cloud for real-time intervention. The third advantage is the low-cost access, which is decoupled from the first stage. Next, let's take a look at the implementation. From the perspective of real-time decision-making, future information is unpredictable and the global optimal solution cannot be determined in advance. In order to solve this problem, we need to consider the estimation and the uncertainty of future information. On one hand, we can decompose the global problem into real-time sub-problems for learning. Here we assume that the data of adjacent time periods are independent and identically distributed. So we can use the data of the previous stage to solve the decision variables to guide the online decision of this stage. Considering that the environment of online application changes rapidly, sub-problems need to be solved with high timeliness. For example, it is minute level. On the other hand, we need to be able to surface a single decision request quickly. In the design of the implementation scheme, we disassembled different technical models, including real-time planning algorithm and online decision service. The real-time planning algorithm takes the snapshot resource of the fixed time segment as sample input and solves the Lagrange multiplied by combing the optimization objectives and constraints of the time period. The online decision service uses the equivalent form of the problem from the linear program duality and takes the dual variable calculated by a real-time programming algorithm as an input parameter to realize faster online serving. Next, let's take a look at the implementation of real-time planning algorithm. In the technical scheme of real-time planning algorithm, four algorithm models are designed around the control of precise budget control and revenue estimation. The first algorithm is correction training. In the first stage of model scoring, there is a gap between the scoring result and the real target score due to the distribution diversion of model training samples. The purpose of correction training is to make the model scoring result as close as possible to the real target score. The second algorithm model is real-time concentrate collection. Considering the uncertainty or lack of the consumption of some resource, we need to combine the actual consumption of resource to correct for the expected budget consumption progress in real time. The third algorithm model is allocation training, which is estimated the traffic of the scenario and activity in the future and splits the total budget objectives and constraints in real time, combined with the real-time constraint collection results. The fourth algorithm model is online LP optimization, which takes the snapshot results of model scoring in a fixed period of time as the sample input, corrects the scoring results by using the correction training model, and optimize the solution by comparing the corrected data with the objectives and the constraints of the allocation of training output and calculates the dual variables. After introducing the scheme of online resource allocation, let's take a look at its architecture, design, and advantages based on RealTime. First of all, let's take a look at the logical architecture of RealTime-based online resource allocation system. The system will serve marketing, advertising, recommendation, search, and other business scenarios, and provide external service such as target and constraint configuration management, online rank service, data dashboard, and so on. In the aspect of algorithm, we have abstract the models of calculation, traffic prediction, constraint reorganizations, optimization with convergence. Different algorithm models can be customized. All algorithm models are implemented based on Real native API and Real framework, such as streaming, surfing, iterative calculation, GPU acceleration, collective communication. The cluster is deployed in Kubernetes. Next, let's take a look at the physical architecture based on Real. The online resource allocation solution involves complex engineering implementation relying on offline and real-time data. The algorithm implementation rests on streaming, surfing, iterative calculation, and GPU acceleration. The whole implementation of real-time planning algorithm includes 5 parts. The first part is constraint collection. There will be some gap between the final result of business system resource allocation and the result of algorithm decision. The constraint achievement can be accumulated by using streaming, and the real-time constraint achievement can be provided to allocation training. The second part is allocation training. It uses the time series model to predict the future traffic data through the historical data, and then use the iterative calculation to disassemble the target and constraint in real time. And the disassembled target and constraint model is written into the cache. The third part is collection training. It uses iterative calculation to train the collection model through historical data, and the model is written into the cache. The fourth part is online LP optimization. It uses streaming to process the real-time data of scoring snapshot generated in the first stage to generate batch samples. When the LP solution cycle is reached, streaming sends batch samples to surfing. After receiving batch samples, surfing uses them to solve LP optimization problems. We use the replacement group feature to deploy the source actor on the GPU machine and use the GPU to parallelize the algorithm. The fifth part is online decision service. Online decision service reads dual variables generated by online LP optimization from the storage for online rank. Online decision service has a high requirement for SLA, so we build an online service framework surfing based on Real. The framework allows users to publish any business logic as on an online surface and control traffic. Users don't need to care about the resource deployment, resource scaling, and cluster disaster recovery. Next, let's take a look at why online resources allocation system choose RE. We built an online resource allocation system based on RE has 3 advantages. The first advantage is that RE provides a simple and easy-to-use API, so developers can quickly implement the app framework. For example, we just use 50 lines of code to implement the iterative calculation of bulk synchronized parallel mode. The offline, nearline, and online links involved in online resource allocation are all implemented based on RE, which greatly reduces the learning and maintenance cost of development. The second advantage is that RE supports convenient resource scheduling. Through placement group, I/O operations, and GPU support, algorithms can be easily developed to the nodes of corresponding resource to make full use of heterogeneous acceleration. Compared with just using CPU, the performance of algorithm can be improved dozens of times. The third advantage is that RE provides efficient distributed fault tolerance. RE acts have second level fault tolerance recovery ability and can sense where the remote calling act is abnormal within 1 second, so it can forward the request to other alive actors, ensuring the availability of the service. At present, LP optimization problems with hundreds of constraints are solved in seconds based on RE. Using a single GPU card. With the increase of business constraints, we will implement a multi-card LP solution based on RE collective communication capability in the future, and explore machine learning to accelerate the solution of optimization problems. This is the end of my sharing. Thank you.